Hello, today we are going to be deriving equations for projectile motion, specifically finding the height, the maximum height, and the range of projectile travels, given its initial velocity and its angle above horizontal. Now, these equations only work when it starts and ends at the same height, and when gravity is the only force acting on the projectile for the duration of its flight, meaning that air resistance or drag is neglected. So when we have uh, a flat surface or flat ground here, because the projectile has to start and end at the same height, we have a projectile going at an initial velocity v0 at a certain angle theta above horizontal. Now this projectile is going to follow a parabolic path and end up at some distance away from its initial position. So we'll call this distance r for range. Additionally, in the middle of its path, it's going to reach the highest point in its trajectory, which we will call h. Now to analyze this motion, we need to split this initial velocity into its x and y components. So along the x-axis, we have the initial x velocity, and along the y-axis, we have the initial y velocity. Now redrawing this out to the side here, we have the initial velocity, the initial x velocity, and then I'm going to put the y velocity vector here. This is the initial y velocity. And then here is an angle theta. From this, it is evident that using trigonometry, we can find that the initial x velocity is equal to v0 cosine theta, and the initial y velocity is equal to v0 sine theta. Now, recall the kinematic equations. The time of flight for a projectile solely depends on its motion in the y direction because gravity acts solely in the y direction. So the velocity in the y direction is equal to negative g, which is the acceleration, since velocity acts downward, gravity acts downwards. So negative g times time plus v0y, or as we have found up here, v0 sine theta. At the top of a projectile's trajectory, the y velocity is going to be equal to 0 because it switches from going upwards to going downwards, which means that when the y velocity is 0, so 0 equals negative gt plus v0 sine theta, the time it takes to get to the top of its trajectory is equal to v0 sine theta over g. So this is the time it takes to get to the top of its trajectory. Now, if you look at the equation for the y position of a projectile, you see that y is equal to negative 1/2 gt squared plus v0 sine theta t. Notice that this is a parabola, and it's going to be symmetric about its vertex. Now, the vertex is going to be the highest height. Now, what this means is that since it's symmetric, the time it takes from the start to its highest point is going to be the same as the time it takes to get from its highest point and fall back down to the ground, which means that the total time of flight is going to be 2 times the amount of time it takes for it to go from the start to its highest point. So the time of flight, so t total, is equal to 2 times this value found up here. So it's 2 v0 sine theta over g. Now, its motion in the x direction, since there's no acceleration in the x direction, can simply be described as the x position is equal to v0 of the initial x velocity. So v0 cosine theta times t. And substituting it for t total to find the range, as in the x position after it travels for its time of flight is equal to v0 cosine theta times 2v0 sine theta over g. And so the range is equal to 2v0 squared sine theta cosine theta over g. Now, if you remember trig identities, you should know that sine of 2 theta is equal to 2 sine theta cosine theta. So that means the range is equal to 2v0 squared sine theta cosine theta over g, as we have found, but it is also equal to v0 squared of sine 2 theta, so v0 squared times sine 2 theta over g. So this is the first equation that we have derived. An important thing to notice about this is, and this is especially apparent if you graph it, is that the maximum range a projectile can reach with a given initial velocity occurs when theta equals 45 degrees. Additionally, if an angle is an amount off of 45 degrees, it will have the same range if it's the same amount off in either direction. For example, 35 degrees is 10 off of 45 degrees, and 55 degrees is also 10 degrees off of 45 degrees. Now, even though they're 10 degrees off in different directions, 35 degrees and 55 degrees will have the same range as long as the initial velocity is the same. And this is due to the graph of sine 2 theta or sine theta cosine theta, and it is symmetric about 45 degrees when theta equals 45 degrees. So now, finding the height of a projectile, maximum height reached, remember that the y position of a projectile is equal to -1/2 gt squared plus v0 sine theta t. And instead of the time of flight, so the total time, we only want the time it takes to reach the top of its trajectory, which we've already found here as v0 sine theta over g. So we have the time to reach the top is equal to v0 sine theta over g. Now, plugging this in, we have the height, maximum height of a projectile is equal to, I'm going to rearrange the terms here, v0 sine theta, so this is the second term, times v0 sine theta over g, so this is our substitution, minus 1/2 g of v0 sine theta over g squared. And so this is equal to v0 squared sine squared theta over g minus 1/2 g times v0 squared sine squared theta over g squared. Now, you should notice that the g here on top cancels with 1g on the bottom. And so this is equal to v0 squared sine squared theta over g minus 1/2 of v0 squared sine squared theta over g. Now from this, it should be evident that the height, maximum height the projectile reaches is equal to v0 squared sine squared theta over 2g. One thing to notice from this equation is that the maximum height a projectile reaches is only dependent on its y velocity. So it's only dependent on its initial y velocity and the gravitational acceleration, which means that its initial x velocity does not impact its maximum height, which makes sense because its initial x velocity does not affect its motion in the y direction. Now, another relation we can find is the relationship between its maximum height and range. So if we take the maximum height divided by the range, we have v0 squared sine squared theta over 2g, and then we can multiply by the reciprocal of the range, which is equal to g over 2 b0 squared sine theta cosine theta. Now, a lot of terms cancel out here. So the g's cancel, b0 squared cancel, and 1 sine theta cancels. So we are left with 1 over 2 times 2 times sine theta over cosine theta. And from this, you can see that the height divided by the range is equal to tangent theta divided by 4. Now, the thing to notice about this is that the shape of a trajectory, so the shape of the flight path of a projectile, is only dependent on its angle and is not dependent on its velocity, initial velocity. So if a projectile has the same angle as another, then it'll follow the same shape of flight, but it might not necessarily follow the same size. So the initial velocity scales up the shape of its path, but it doesn't affect the shape itself, only the angle does. So to summarize, we have the range of a projectile is equal to 2v0 squared sine theta cosine theta over g, or v0 squared of sine 2 theta over g. The maximum height a projectile reaches is equal to v0 squared sine squared theta over 2g, and the relationship between height and range, so height divided by range, is equal to tangent theta divided by 4. Now, as a reminder, these equations only work when a projectile is only under the influence of gravity, which means that there's no air resistance, so no drag forces, and it only works if the projectile starts and ends at the same height. Right, thank you for watching.